Hello, Stat 200, and welcome to Lesson 7. This is the second of two lessons on confidence intervals. In Lesson 6, you learned how to construct confidence intervals using bootstrapping methods. This week, we'll use more traditional methods. You'll learn how to construct a confidence interval for a proportion or a mean using formulas and Minitab Express. Let's begin by reviewing the general form of a confidence interval. This is the same form of a confidence interval that you've seen in the last two lessons. The point estimate this week is still going to be the sample proportion or the sample mean, plus or minus the multiplier, which varies depending on your level of significance. In previous lessons, you used multipliers from the z distribution and you applied the empirical rule. This week, when we're constructing a confidence interval for a proportion, we'll use the z distribution again. However, when we construct a confidence interval for a mean, we'll use a similar distribution, the t distribution, times the standard error, which is the standard deviation of the sampling distribution. Last week, you used bootstrapping methods to compute the standard error. This week, we're going to go back to what you saw in Lesson 5. Recall, if certain assumptions are met, then the standard error of the sampling distribution of p hat or x bar can be estimated using the rule of sample proportions or the central limit theorem. Again, to review the last two lessons, in Lesson 6, bootstrapping methods were used to make a bootstrap sampling distribution. You use that standard error to construct a confidence interval using the standard error method, or you use the percentile method to find the middle 95% of that sampling distribution. The week before that, in Lesson 5, you learned that if certain conditions are met, the sampling distribution will be approximately normal. Recall, for proportions, if n times p and n times 1 minus p are both at least 10, then the sampling distribution will be approximately normal with a mean of p and a standard deviation of the square root of p times 1 minus p divided by n. For means, if the population is normally distributed, or if the sample size is at least 30, then the distribution of sample means will be approximately normal with a mean of mu and a standard deviation of sigma divided by the square root of n. We're going to see these formulas again this week. These are the key topics that you're going to see in Lesson 7. First, we're going to construct confidence intervals for a proportion. I'll show you how to use the normal approximation method both by hand and using Minitab Express. You'll also learn how to use the exact method in Minitab Express. The exact method approximates the sampling distribution using a binomial distribution. We're not going to construct these by hand. We're only going to do them in Minitab Express. And then you'll learn how to compute the necessary sample size to construct a given confidence interval. For example, if you wanted to construct a confidence interval for a population proportion with a margin of error of 2%, what minimum sample size should you obtain? For confidence intervals for a mean, you're going to learn how to use the t distribution both by hand and in Minitab Express to construct a confidence interval for a population mean, and we'll also look at computing the necessary sample size for constructing a confidence interval with a given margin of error. I want to start by showing you a flowchart that summarizes the methods that you're going to see this week. For a proportion, recall if n times p and n times 1 minus p are both at least 10, then the sampling distribution will be approximately normal. In those cases, we'll use the normal approximation method. If that assumption is not met, then you'll use the exact method. This approximates the sampling distribution by a binomial distribution. We're not going to do this by hand this week, but you will see how to do it using Minitab Express. For a mean, if the sample size is at least 30, or if you know that the population is normally distributed, then the sampling distribution can be approximated using a t distribution. If this assumption is not met, then you should use the bootstrapping methods that you learned last week. Let's start by looking at a confidence interval for a proportion. Recall from Lesson 5, given that n times p and n times 1 minus p are both greater than or equal to 10, The distribution of sample proportions will be approximately normal. That distribution of sample proportions will have a mean that is equal to the population mean, and a standard deviation, also known as the standard error, that is equal to the square root of p times 1 minus p divided by n. This week, you're going to be working with cases in which you do not have the population proportion. In these cases, you'll only have a sample proportion, in which case, the population proportion p that you see in these formulas is estimated using your sample proportion. For example, the standard error formula would be the square root of p hat times 1 minus p hat divided by n. Here's our formula for the confidence interval of p using the normal approximation method. Our point estimate is our sample proportion. Our multiplier is a z multiplier. This is a value from the normal distribution. In your online notes this week, you have a table of the most commonly used confidence levels and their associated z multipliers. The one that we've been working with most to this point, and the one that you'll see most often in real life, is the 95% confidence interval. The z multiplier is often rounded to 2 via the empirical rule, although the precise z multiplier for a 95% confidence interval is actually 1.960, which is what you'll see me use this week, and is also what Minitab Express is going to be using in its calculations. Finally, the standard error. Recall, because we do not have the population proportion, we're going to estimate it using our sample proportion. So our formula for the standard error is going to be the square root of p hat times 1 minus p hat divided by n. Let's look at an example. In a random sample of 100 newborn babies at one hospital, 54 were female. Estimate the proportion of all newborn babies at this hospital that are female at the 95% confidence level. We're given n equals 100, x equals 54, so p hat equals 54 over 100, which is 0.54. N times p hat equals 54, n times 1 minus p hat equals 46. Both of these values are at least 10, so we can use the normal approximation method in this scenario. Here's our formula using the normal approximation method. Going back to the table from the online notes, we know that the z multiplier for a 95% confidence interval is 1.960. Our standard error is equal to the square root of p hat times 1 minus p hat over n. This equals 0.0498. We can plug these values into our formula for the 95% confidence interval, and we get 0.54 plus or minus 1.96 times 0.0498. When we do these calculations out, we get a 95% confidence interval of 0.442 to 0.638. I could also say that I am 95% confident that between 44.2% and 63.8% of all babies born at this hospital are female. Let's go to Minitab Express really quickly so I can run through this same example there. In Minitab Express, we're going to conduct a one sample proportion confidence interval using summarized data. In our sample, there were 54 females out of 100. We are not going to perform a hypothesis test at this point. You'll learn about hypothesis tests in the next two lessons. The default is a two-tailed confidence interval, which is the only type of confidence interval you'll see in this class, at the 95% confidence level. Both n times p and n times 1 minus p were at least 10, so we need to change the method to the normal approximation method. When we click OK, we get a 95% confidence interval of p of 0.442 to 0.638. The confidence interval that you get using the normal approximation method in Minitab Express should match the one that you get using the hand calculations, also using the normal approximation method. What we just saw was an example using the normal approximation method. This method can only be used if n times p and n times 1 minus p are both at least 10. In cases where this assumption is not met, the exact method should be used. There is no sample size assumption for the exact method. Using this method, the sampling distribution is a binomial distribution. We're not going to do these calculations by hand because if you recall from lesson 4, the hand calculations for binomial probabilities can get quite involved. Instead, you'll just learn how to do this in Minitab Express this week. Let's look at one quick example. In a random sample of 30 students, 27 passed a recent exam. Estimate the proportion of the population that passed at the 95% confidence level. So n times p hat is 27, but n times 1 minus p hat is 3, which is not at least 10. So we're going to use the exact method. Let's go to Minitab Express again. Again, we're going to conduct a one-sample proportion confidence interval. We have summarized data. There were 27 out of 30 students who passed. Under options, we're going to construct a 95% confidence interval, and because n times 1 minus p hat was not at least 10, we're going to use the exact method, which is the default. Here's our 95% confidence interval for p. I am 95% confident that the proportion of all students who would pass this exam in the population is between 73.5% and 97.9%. The last thing that you're going to work with related to confidence intervals for proportions this week is estimating the necessary sample size. The z with the asterisk that you see in this formula is the z multiplier. Again, here's the table from your online notes for the most common confidence levels. If you're working with a confidence level that is not on this table, you can use Minitab Express to construct a probability distribution to find the z multiplier. P hat is the estimated population proportion. If there is no estimate of the population proportion, you're going to use the most conservative value, which is 0.50. Let's look at an example. We want to construct a 95% confidence interval for the proportion of Americans who drink soda on a daily basis with a margin of error of plus or minus 2%. We're constructing a 95% confidence interval, so our z multiplier is 1.960. We're given a margin of error of 2%, so m equals 0.02. We're not given an estimate of the population proportion, so we're going to use the most conservative value, 0.50. Plugging these values into our equation, we find n equals 2,401. So if I want to construct a 95% confidence interval with a margin of error of 2%, I should obtain a sample size of at least 2,401. Now let's look at a confidence interval for a mean. Recall, if n is at least 30, or if we know that the population is normally distributed, the sampling distribution will be approximately normal, and we can estimate it using a t distribution. The t distribution is similar to the z distribution in that it is symmetrical. However, it varies depending on degrees of freedom. For a one-sample test, degrees of freedom equals n minus 1, so the sample size minus 1. As n increases, the t distribution becomes more similar to the standard normal distribution. So as your sample size approaches infinity, the t distribution approaches the z distribution. Here's our formula for a confidence interval for a population mean. Our point estimate is x bar, our sample mean. The multiplier that we're going to use will come from a t distribution with n minus 1 degrees of freedom. And our standard error is equal to the standard deviation divided by the square root of the sample size. Here's one example. In a random sample of 35 students, the mean quiz score was 13.2 with a standard deviation of 3.1. Construct a 95% confidence interval for the mean quiz score in the population of all students. Here's our formula. We're given a sample size of 35, a sample mean of 13.2, a sample standard deviation of 3.1. Our degrees of freedom will equal n minus 1. 35 minus 1 equals 34. We need to construct a t-distribution to find our multiplier. So let's go to Minitab Express to construct that probability distribution. We'll construct a probability distribution plot to display a probability. We have a t-distribution with 34 degrees of freedom. We're conducting a 95% confidence interval. So the middle 95% will be separated from the outer 5%. Here's our t-distribution plot, and our multiplier is 2.03224. We can plug these values into the formula. So 13.2 plus or minus 2.032 times 3.1 divided by the square root of 35 gives us a margin of error of 1.065 and a 95% confidence interval of 12.135 to 14.265. To interpret this, I would say that I am 95% confident that the mean quiz score in the population of all students is between 12.135 and 14.265. Again, I'm going to go to Minitab Express to show you how you could construct this confidence interval there. Now, we're going to construct a one-sample confidence interval for mu using the t-distribution. We have summarized data. We had a sample size of 35, a mean of 13.2, and a standard deviation of 3.1. Under options, the default confidence level is 95%. Our 95% confidence interval for mu is 12.1351 to 14.2649. And again, the last thing that you'll do this week involving confidence interval for means is to estimate the necessary sample size. Because the t-distribution varies depending on degrees of freedom, we're going to use a z-multiplier in this formula. The value of the z-multiplier, if it's a common confidence level, can come from this table. If it's not one of these confidence levels, you can use Minitab Express to construct a probability plot to find that z-multiplier. Most commonly, you're going to be constructing a 95% confidence interval, which has a z-multiplier of 1.960. The sigma with a tilde that you see in this formula is the estimated population standard deviation. You need to have some estimate of the population standard deviation in order to estimate the necessary sample size. This often comes from a pilot study or from a study that uses a similar sample. Let's look at one example. We want to construct a 95% confidence interval for the mean height of all World Campus students with a margin of error of 2 inches. In a sample of World Campus Stat 200 students, we found a mean of 66.798 and a standard deviation of 4.594. We can use this standard deviation from a sample of World Campus Stat 200 students as an estimate of what the population standard deviation will be. So the sigma with a tilde, or the estimated population standard deviation here, will be 4.594, because that is the best estimate that we have at this point. We're constructing a 95% confidence interval, so the associated z-multiplier is 1.960. We have an estimated population standard deviation of 4.594. and we're given a margin of error of 2. We plug these values into our formula, and we find n equals 20.269. We cannot have 0.269 of a World Campus student, so we're going to round up. In this case, we would want a minimum sample size of 21 World Campus students. Those are all of the new procedures that you're going to learn this week. Now let's go back and review when to use each of them. Question that you're going to see this week is, how should we approximate the sampling distribution? In other words, which method should you use? Normal approximation method, exact method, a t-distribution, or a bootstrapping method? For one proportion, the question you need to ask is, are n times p and n times 1 minus p both at least 10? If yes, then the sampling distribution can be approximated using a z-distribution. This is known as the normal approximation method. If no, then the binomial distribution should be used as an approximation of the sampling distribution. In Minitab Express, this is known as the exact method. Note that you could also use bootstrapping methods in this case. For one mean, the first question that you can ask is the population normally distributed? If yes, the next question is the population standard deviation known? We're not going to cover this in this class, but if the population is normally distributed and the population standard deviation is known, then the sampling distribution would be approximated using a z-distribution. This is most commonly seen in the social sciences when you're working with standardized tests, which are normed to have a given population mean and population standard deviation. In other fields, you're not going to see this as often. If the population is normally distributed, but the population standard deviation is not known, then you would use a t-distribution. If the population is not normally distributed, or if you don't know the shape of the population, the next question you would ask is the sample size at least 30? If yes, then you could still use the t-distribution. Because according to the central limit theorem, if the sample size is large, typically greater than or equal to 30, then the sampling distribution will be approximately normal, and the t-distribution is appropriate for use. If the population is not known to be normal and the sample size is smaller than 30, then you should use the bootstrapping methods that you learned last week. I recommend that you make yourself a copy of this flowchart and keep it with you as you're working through the homework, quiz, and lab assignment this week. You may also want to put it on your sheet of notes that you can take with you to the proctored exams. As always, if you have any questions as you're working through the homework or lab assignments this week, you can post them to the Lesson 7 discussion board on Canvas.